Let's look at the land carbon uptake as well. Again, starting with this figure, which is very handy. You can see that the total emissions have obviously been increasing, and the ocean uptake has increased and land uptake has increased. We showed maps of land ocean PCO2 and air CO2 fluxes and the interannual variability, and talked about how difficult it is to map it because you need lots of data. So on land it's a similar problem. I mentioned flux towers, but the ocean is much more homogeneous on a larger scale. Even though there are eddies and they can make some difference in the AC exchanges and surface ocean PCO2 and so on, the land is very inhomogeneous in terms of land use change from one spot to another: agriculture, forests, different crops, urbanizations, rural areas, wildlands, abandoned lands, and so on and so forth, degraded lands, and so on and so forth. Looking at this figure again about the perturbations between 2010 and 2019, you begin to get some sense that making a global map of CO2 fluxes for the land, similar to the ocean, is also going to be quite a challenge. The timescales are also going to be much faster over the land than on the ocean, and you expect a stronger diurnal cycle as well, day and night. So here, for example, let's again ignore the reserves and look at permafrost. Okay, we will come back to this later on in terms of what can be expected in the future. Soil permafrost is typically obviously limited to the northern hemisphere, Arctic Circle kind of latitudes, and they are thawing and they are beginning to emit CO2 and methane, which we will touch on later. These are the global average numbers, 120 in and 120 out, with an uptake of 3.4 gigaton carbon over this period. The vegetation estimate is 450 to 650 gigaton carbon, and you can imagine the uncertainty is quite high. And you have wildfires where you can emit huge amounts of carbons, like especially the very vast, devastating fire in Australia, or the seasonal fires over parts of US, and the one that was burning just a few days ago over South Africa, Cape Town, made it all the way into the library, and so on and so forth. And soils are very heterogeneous. Even in a same little village, you can have soil properties and soil carbon varying a lot, even though you can generally say that mid-latitude carbons have slow metabolic rates and have a much higher carbon percentage than the tropical forests, which are have a high respiration rates, and even in heavy rainforest areas the soil carbon is lesser compared to the mid-latitudes. And then you have the river stripping off organic matter, and there is weathering happening, and they are all washing it out into the coasts, and then of course you have shelf areas and so on into the deep ocean. So land uptake at this number even has many components. So in a natural environment you have natural fire cycle. So this is showing atmospheric composition and land surface albedo, sensible and latent heat fluxes, and water vapor fluxes. But we are also looking at increasing and decreasing atmospheric fluxes of carbon dioxide, methane, N2O, NOx, and aerosols, which are the general greenhouse gas and radiative forcing gases that we look at. So you can see that there is uncertainty in terms of vegetation growth, whether it's out or in the natural cycle, including fire cycles. Wetlands have uptake of CO2 but emission of methane, which is a major source of methane, of course, and there are others here which are being emitted, like black carbon and organic carbon and sulfate aerosols and so on. Forests, a lot of debate goes on, especially in the context of planting 1 trillion trees and solving the climate problem, which is opposed by a lot of people. So there is decomposition, putting out fluxes, and vegetation regrowth, which is taking up carbon, and you have, of course, all the other processes like hydrological cycle changes, deforestation, irrigation, nitrogen cycle, which interacts like fertilizers and so on, which interact with the carbon cycle, agriculture in terms of waste burning, food production, wildfire regime. This is the anthropogenic land use and land cover change. So grazing, reforestation, wood harvesting, and so on and so forth. So you can imagine just how non-homogeneous it is to track land uptake. But efforts are made by bookkeeping and by modeling to kind of try to deconvolve some of these details. So here is a model that I will show some results from. So it's showing the forests for deforestation, fire emissions, conversions to agricultural land, abandoning and regrowth or converting back to agriculture, and wood harvesting, burning, and again different kind of fire emissions. There is wood that is emitting carbon by activities that use wood for other activities in human lives, so there is regeneration there as well possible. So basically total land use change emissions are counted as fire, legacy land use issues, wood harvesting, and recovery of forests. Just to give you an example, so the model estimates and the bookkeeping model, which is much more reliant on data and constraints, you can see the results are different. The models, of course, are representing these processes and have time scales, so looks like there is a lot more information here in terms of the wiggles compared to these smoother variabilities here. But one has to be careful because these are not always that well constrained. Nonetheless, in general, we tend to look at this and say the model is performing reasonably well, let's say in terms of total emissions from land use change, combining these different components. Okay, so essentially land use uptake is at the number that we looked at, and the other thing we have to worry about is how we have perturbed it so far. We already said that land is increasingly taking away more carbon, and what we didn't mention so far more explicitly is the CO2 fertilization effect on land, especially where you have lots of vegetation, photosynthesis uptake. There is a competition of the leaves to open the stomatas to take up CO2 for photosynthesis without losing the valuable water vapor that's been moved up by the roots all the way from deeper soils into the leaves at the top of the tree. So as CO2 increases, that stomatal conductance, or the amount of time it has to open, changes. So there is a carbon fertilization effect, which means increasing carbon dioxide tends to make the plants grow faster. It's not very clear always whether that means they are storing more carbon. That's different, so faster growths. Nonetheless, if you look at pre-industrial times in terms of gigaton CO2 per year, you can see the industrial was these recent changes here. We are putting out more industrial emissions, changing land use, volcanic activity continues, weathering continues to draw down. Pre-industrially, we had respiration and photosynthesis essentially balancing over the globe, whereas this is land and sea. So over sea you had 260 in and 260 out, so also fairly balanced. But now land is increased uptake by plants to about 10 gigaton CO2 per year, and the ocean is doing somewhat of a similar number, so it's releasing 70 but absorbing about 80. Okay, so the net accumulation is about 15 gigatons in the system. So essentially we are looking at a carbon cycle that is having a stabilizing effect in our definition of whether increased CO2 by some activities like human activity is amplifying the original perturbation or it is trying to damp it. Obviously, the human emissions of fossil fuels are being damped by the carbon uptake in land and ocean, especially increasing land and ocean uptakes. So now we will switch to the future and see what the future is going to do as best as we can estimate. Will it continue to be a negative feedback even as atmospheric accumulation continues to increase and warming continues to rise, or will it at some point become a positive feedback where the uptake by land and ocean will decrease and accumulation in the atmosphere will accelerate and the global warming will accelerate, and then you will have a positive feedback? That's the key question we are after, of course, right?